So usually hold it up here. Which one?
The PA? No, it's not. Yeah,
Anyone else have a badge in here? Want to know how it works? Yeah. Yeah? You want to know? I'll come out. Sure. How much time do you have before you start? I'm sorry.
Do you need another 5 minutes or?
No, it's okay.
Yeah, we can do it. Go. We can do it.
We'll do it after.
No, it's okay.
Go ahead. We're just passing flags on the ready for you. So.
Let's do it.
Welcome.
Fantastic.
You can go next.
I already went.
Thanks all for your patience. And thanks for coming to hear about WebCrypto. I did ask for a show of hands on who was cryptography inclined. Yeah, a couple folks. And who was kind of more web inclined? A couple folks. All right, cool. I'll introduce myself here. My name is Kat Traxler. You can call me Nook if you'd like. My day job is web application penetration testing. And I also have some relevant experience building mean stack applications. This is where I found a love for JavaScript. Building Mongo, Express, Angular, Node, the full stack JavaScript. It's the kind of love a person has when they see a storm coming and they just really want to go outside and see the lightning. That's JavaScript for me. And I was always really interested in cryptography, but I'd really be classified more as a cryptography tourist than anything. I didn't have to go too far to see a cryptography tourist site because cryptography just kind of came to me. Cryptography in your browser has been around since, the 90s, since TLS, SSL. But what has changed really, is client-side encryption. JavaScript is being enlisted to do some heavy lifting in your browser. Implementations of JavaScript in your browser are things like the Stanford JavaScript crypto library. The Stanford JavaScript crypto library sought to prove that there was no reason you couldn't do cryptographic operations directly in JavaScript. But there's some glaring security gaps that are just inherent to JavaScript. JavaScript, for example, has no strong bindings. JavaScript cannot validate any of its dependencies. Additionally, JavaScript doesn't have any protected variables or protected namespaces. Furthermore, I'm discussing JavaScript as it exists in the browser. JavaScript for the web is bound by its runtime, which is the browser. Missing in the browser is an obvious secure key storage. Without secure key storage in the browser, this is the OS that we have to deal with, right? The browser is our OS now without any secure key storage. Why is cryptography in the browser, right? Like, why are we doing this at all? There's some pretty good reasons why people are doing it. For example, secure document storage, multi-factor authentication, protected document exchange. We've done all of these things server-side for a long time. So the reasons for this aren't special. What's changed is where it's happening. And why is it happening client side? Well, it can be sold to a user as you have more protection over your data now. You have more control. For an application, what happens when you move encryption client side is you limit your burden. You know, I think there's a fallacy that says that your application really wants you to know the contents of your data. They might want your metadata, but they don't really want the contents of your data. If they're served with a warrant for your data, they want to be able to limit their liability. And doing client-side encryption is the perfect way to do that. So this brings us back to the question, what are we asking JavaScript to do? I highlight four goals of crypto. Traditionally, there's the triad of goals, right? Confidentiality, integrity, authentication. Confidentiality, typically you think of encryption. You can also have availability with encryption. If you have reliable decryption, that can bring you some availability. Authentication, integrity, non-repudiation. We meet these with MACs. We meet these with public key cryptography, digital signatures. But we have to understand that all cryptography starts with secure numbers, secure random numbers. Some keys must be random. Some keys need to have more random bits than other keys. Some keys need to be unique. We have nonces, we have salts. These are all cryptographic operations that require a secure random number. So how does JavaScript attempt to overcome its lack of a secure random number generator, its lack of secure random, as you might see in Java, say? There's two different approaches that I'm going to talk about here. One of the approaches actually says we can't trust JavaScript at all to do this. So I'll mention first the Stanford JavaScript Crypto library, the first real solution to this problem. The JavaScript Crypto library devised a solution for collecting entropy from events that happen in the browser, on click, on mouse over, on blur, on key press. These are combined with the times that these events occur. They run it through a whitening function, and you have a fairly decent source of entropy. The other method for obtaining secure random in a browser is the WebCrypto API. And what the WebCrypto API says is, we can't trust JavaScript at all to handle this. We're going to reach outside of the browser for entropy, and those cryptographic operations are performed natively in your hardware. So that's a commentary not on the source of the entropy, not the quality of the entropy that you'll gain from events-driven models, but really is a commentary on the secure source. So a event time-driven source of entropy is only as good as you can trust those times and those events. And what I'm trying to impress upon everybody is that you really can't trust much that happens in a browser. So I'm going to give everybody a little bit of an overview of the WebCrypto API. So the WebCrypto API working group, so it developed a method, like I said, of obtaining secure random outside of the browser. Like I said, it said you can't trust anything that happens in the browser, these events, these mouse clicks. We're going to provide a source for developers to do this securely. Cryptography in the browser was happening, but also JavaScript in the browser needed access to, needed the ability to direct these cryptographic operations. What's really missing from the WebCrypto API is any sort of direction. I'm gonna start out by taking us down a bit of a fictional path. We're gonna do a thought experiment here, and we're gonna pretend we're a developer. And we've been tasked with the idea of creating a feature, and we're going to be encrypting a document for a user. And this user needs to later decrypt this document. So we're left with a few methods. We can encrypt, decrypt, sign, verify. We're accessing the WebCrypto API via the crypto.subtle interface. And the creators of the WebCrypto API meant to say subtle as a hint to everybody that maybe some of these operations have some subtle impact. But as this developer, let's say we're going to start out, we're going to encrypt this document. But first we need a key. Let's take a look at generating keys. When we generate a key through the WebCrypto API, we have a few choices that we're presented with, and the WebCrypto API attempts to limit our abilities to shoot ourselves in the foot. Right, so when you are creating a symmetric key, the only algorithm available is AES. That's all we have. And in fact, if you don't want to specify a key length when creating a key, 256 is what it defaults to. In addition, you need to indicate if this key is going to be extractable or not, and its usages. Now, whether or not what mode you choose of AES, this choice is definitely full of pitfalls, and I'm going to skirt the choices right here and just say that it's not a unique problem to WebCrypto. However, whether or not a key is extractable out of a browser is very unique, and so this is what makes this new. A little bit more on what's created when we are going to be creating the symmetric key. When we create our symmetric key, this object that we're going to be creating, it's going to be a limited object. It's not going to be available to be accessed by. It's not going to be available to be accessed or stored in local storage. We can't save it as a cookie. We're not going to be allowed to write it. It's going to be a read-only object. The value is not actually going to be known to the browser if we want to create it as a non-exportable object. It's going to be tied specifically to that browser that it was created in. The WebCrypto API has not rewritten the rules of the web. When you create a key with the WebCrypto API, the same origin policy applies. So you can send this key cross-domain. Now, I put a big caveat around you can't send this key cross-domain because cross-domain web requests happen every day, and that's through a thing called CORS, the cross-origin resource policy. So if a application implements CORS incorrectly, and you create this WebCrypto key as an extractable key, it can certainly be sent cross-domain. So we've created a key for a fictional feature, and maybe we should create it non-extractable. Extractable means that we could send it, we could transmit this key. Non-extractable means that it needs to live in the IndexedDB. So maybe we keep it non-extractable. We keep it the safety first choice. What do we do with this key now that we have it? We probably want to use it to encrypt our document. That makes sense. So we're going to encrypt the key. We're going to encrypt our document with this symmetric key, and we're going to keep the key non-exportable, and we're going to keep it tucked away in our IndexedDB. And our user's document can be encrypted, and it can be sent off to the server to be saved, and we have a perfectly good encryption scheme. But something doesn't seem right here, and maybe some folks are following along with this, that key to then decrypt the document is hanging out at IndexedDB. IndexedDB is not going to hang around forever. The user can certainly clear IndexedDB and their document is gone. This is not a usable feature. Web workers can come by and clear out IndexedDB. So what's going to actually happen in practice? The symmetric key that we created to encrypt the document, and we thought it'd be a really safe idea to keep it non-extractable so it can't be sent cross-domain. Actually, we have to make it extractable because we're going to use another function of the WebCrypto API and we're going to wrap it. So we're going to create a key from the user's credentials and we're going to wrap this key and we're going to send it along with the document and then it'll be returned and you can unwrap the key and then use it to view the document. Unwrapping and wrapping a key, it's a very common cryptographic practice. And there's a fun function of the WebCrypto API that actually allows you to change a key's usage at that moment. So the WebCrypto API really tries hard to prevent us from shooting ourselves in the foot. However, at that moment, we could specify the key to be a signing key, which, if you know anything about cryptography, is a horrible idea to do with a key that is also used to encrypt. And we're not also going to be using the WebCrypto API directly. I'm sorry. This path that I led you down actually doesn't really happen in practice. What happens in practice is developers use libraries that are abstraction layers. And here's just a handful of the libraries that have sprung up to support WebCrypto. Forge.js, Clipper.js, Polyfill, ASMCrypt, OpenPJP.js. And some of these tout themselves as pure JavaScript implementations. And if you ever see those words, pure JavaScript implementation, you know that it is a event-driven model. It's not calling the WebCrypto API directly. What most of those libraries do is they're actually more of a hybrid. So I'm going to highlight 3 different libraries. I'll talk about 3 different libraries, and I have just a chunk of code up here because I thought it was the most egregious. I don't know if anybody's heard of Clipper.js. Clipper.js is a browser extension, password manager. It really touts you. They never know about your data. Your data is never sent to their servers unencrypted. Well, they're a pure JavaScript implementation. They derive their source of entropy from user events. Then there's a more of a hybrid method, which I have up here. So OpenPGP.js, ProtonMail is actually the maintainer of that open source project right now. It does first attempt to access the WebCrypto API project, the WebCrypto API, and then it thinks maybe I'm hanging out in a node server. Maybe I should get my source of entropy from this node object. No, finally, okay, well, maybe whoever called this function has a random buffer. Maybe I will use that for my entropy. So if anybody here has some wonderful ideas about server-side includes or any kind of JavaScript injection for this, we should talk afterwards because this has got me really excited. And the last bit that I will mention is PKI.js. PKI.js does have a strict WebCrypto API implementation. However, on their GitHub, they do admit that their library is somewhat limiting, and you're probably even going to actually have to use a shim, and they point you directly to the shim you're probably going to have to use to make your feature even usable. So what do I have to say to all this? The takeaways that I hope you have are that cryptography is complicated stuff, right? And the way software is developed is that people build it and then they test it and they fix it until it doesn't break their nightly builds anymore. And somebody's, insecure random number generator never broke anybody's builds. It's a quiet fail. And if you find yourself reviewing some web crypto and it seems like they're implementing everything right, don't worry, everybody. You can just break the client. Thanks.